So, last class I discussed with so what are the things I discussed last time? Huh? Wigner function. Okay. So, I introduced Wigner function. Okay. So, what I am going to do today is um, uh, uh, so, I will introduce the notion of displacement operator, which I think I mentioned earlier, and then try to express any operator as a linear combination of the displacement operator. Okay. And then this will be helpful in getting different phase space distribution functions of our density operators. Okay. Right. Okay, good. So, to begin with, if I take this harmonic oscillator Hamiltonian, one dimensional harmonic oscillator Hamiltonian, p square by twice m plus half m omega square x square. So far I have not used this m omega etcetera, but we will not use it later also, but for the timing let me use it. Now, let us assume this, perhaps you all know that if I, so this is my harmonic oscillator, okay. This is the one dimensional motion, and let us say this is the position of the oscillator at a distance x, and let us assume that a charge q is also sitting on this particle harmonic oscillator. Okay. And so, apart from these harmonic motion, that is the harmonic potential, this is also being acted upon by, let me write it here, by a constant electric field. Okay. So, if you want you can call it as E 0. So, it is a constant electric field. Then I know that there will be, so this is my original Hamiltonian. Now, the change Hamiltonian will be p square by twice m plus half m omega square x square minus q E naught. So, I do not have to put this because this is along the x axis, E naught x. Is that okay? Right, because of this potential. And as a result, you know that this is nothing but omega square x square and minus twice q E naught by m omega square x plus q E naught by m omega square to make it perfect square, and then minus what will be that q E naught square divided by twice m omega square, right. I mean to make it a perfect square. So, now I can call these, so this is my x minus q E naught by m omega square whole square, okay, and whatever else is there. So, this is basically, if you take this is a constant energy. So, I can shift this energy, it does not make much difference except that I will have to shift my energy levels. Then this is basically, so if I look at this Hamiltonian H prime, which is p square by twice m plus half m omega square x minus q E naught by m omega square. So, this is like this original harmonic oscillator Hamiltonian, but with a shift in origin. Okay. So, this transformation that I take x to x minus q E naught by m omega square, this is a translation along the x axis, but in order to make it a canonical transformation, I will also have to transform this P, right, because canonical transformation means you will have to take both transformation on x and P, linear canonical transformation. So, this should go to P itself, because I have not done anything here, and you can see that if I call it as, let us say, x prime hat and this as P prime hat, then x prime and P prime, they satisfy the same canonical commutation relation as x and P. So, this is indeed a canonical transformation, right, and this canonical transformation at the level of Hamiltonian, if I start from this Hamiltonian, see this is just a constant shifted energy. So, I do not bother about that. So, from here to come to this Hamiltonian, okay, what is it that I will have to do operationally? Physically I am translating the particle along the x axis by this amount, but at the level of state space, what is it that I am doing? Which operator I should apply?
Position translation.
Position translation. And what is that? So, I will have to look for the unitary, because this is continuous transformation. So, I will have to look for the corresponding unitary operator. Okay. And what is that corresponding unitary operator? Which will perform these operations?
E to the power I P.
Yeah. So, the momentum is the generator of this, right. So, therefore, e to the power minus I q E naught by m omega square p. I should put h cut, that is okay, right. So, this is my operator that will do the job, right. So, if I apply this operation on this Hamiltonian, I should get back this, right. So, now if I want to look at, so you know that I can express P in terms of A and A dagger, right. I mean, I will have to be little bit careful about the units, because so far I have been using this dimensionless position and momentum, but this can also be done, right. So, therefore, you see that this operator is basically, so minus iota, okay. Then okay, now what will be the, can you tell me what will be the form of P in terms of A and A dagger?
Minus I comes to A minus A plus A dagger, that's some P, right? P is minus, right?
Remember, this is not the dimensionless momentum operator. So, dimensionless momentum operator I have used as P hat, but anyway this will be basically some specific linear combination of A and A dagger, right. So, for the time being we can forget about that. So, this I can write therefore as exponential of some specific form, so which I will call alpha A dagger and then minus alpha star A. Now, why this specific form? If you write this P in terms of A and A dagger, you will get this one. It is not. So, this is very very specific form. Okay. In fact, here you will see that this alpha will be basically a real number for this case. Okay. Anyway, so generic form. So, this is along x axis I am displacing, but if I do this thing, so this is my x and p, if I do along certain direction, not necessarily along x axis, then the most general form of displacement operator will have this thing, will be of this form. Okay.
It should come with a minus sign P hat.
Which one?
P hat is actually A dagger minus A times some scalar.
No, P hat is not that simple form. P hat, because this is this has dimension. So, what I discussed so far is this thing, x is equal to A plus a dagger by root 2 and p is equal to iota a dagger minus a by root 2, but this x is related to this x with some factor here, right. Similarly, this p is related to this p with some factor.
I think your I and I will get that will be plus, I think, right? Minus I times I. That will be
Yeah.
plus.
So
Because these small x and small p have their dimensions, and you will have to take care of these factors also. Maybe this is like square root of m omega by twice h cut, something like that. Okay. So, if you take care of that, then this is the form you will get.
okay. Yes. You're right.
In fact, this is for displacement along x direction, but any generic direction in the phase space, if you express the corresponding operator in terms of a and a dagger, it will have this form,
Yeah.
where this alpha is a complex number.
In this case, it will be a real number.
In this case, it is a real number. Yes. Yes. Okay. Right. So, this displacement operator d of alpha, which is exponential of alpha a dagger minus alpha star a for any complex alpha. So, what does it do? Basically, in this case, if I take the ground state, so if I take the ground state, minimum energy state of this, then the ground state of this Hamiltonian, which I call 0 prime. So, this is related to this one, d alpha acting on 0. Okay. So, basically it is displacing the ground state of this original Hamiltonian. So, generically I can say this is the ground state of the original Hamiltonian, harmonic oscillator Hamiltonian, or say quantized single mode quantized electromagnetic field. So, this I will call it as alpha, and you know that. So, there are certain properties that you can satisfy. One is that d of alpha is unitary. So, so dagger of this, what is this dagger? This is exponential of alpha star a dagger. What will be this dagger of this? Minus alpha, right? And d of alpha dagger, d of alpha is equal to what? Because this is just negative of this. So, you can just add them. So, this will be identity. So, which is d of alpha dagger is equal to identity. So, this means that this is nothing but d of alpha inverse also, right. So, this is unitary operator, this d of alpha. So, as a result, this evolution is unitary evolution. Okay. So, displacing a your physical system in the phase space corresponds to this unitary transformation.
displacing under this magnetic field.
Displacing under electric field, but you can take any direction. I have taken in along x, any direction you can take.
So, if you apply some other field, then it might not be unitary.
Which field?
Let's say some dissipative field.
No, of course not unitary, but this is very specific. You apply the electric field, okay, because you know that this gives rise to this translation. Okay, so if you apply even here, if you apply both electric field and magnetic field, it will not be of this form. Okay. So, this applying electric field means, well, even if it is magnetic field, the same is true. You are inserting some energy, and that gives rise to your displacement. Classically also that is what we do. Okay. So, now what is important?
Sir, what exactly is the equivalence here? Let's say, for example, initially we had the particle localized x without this electric field.
Yes.
So if we apply the electric field, and then let's say we have some initial state, then we'll find that the new center is shifted
Yes.
for this oscillation. So this is one case. The other equivalent case in which you apply unitary, what would that be? Like
No.
this d alpha unitary.
Yes.
So you have initially particle localized x is equal to 0 only, and then what exactly do you do? Do you evaluate using this unitary?
No. See, what we have done here is, so classical, let's look at the classical picture. You have a spring, okay, so which is, no, it has a center of it has a equilibrium point, right, okay, about which it oscillates. Now you know take away the center equilibrium point to a further point, okay, right. So that it will oscillate about this new equilibrium point. So, it is a kind of displacement, and this you have achieved by applying some force, I mean some amount of energy you have applied, right, which is this electric field here. Now, if you want to do it quantum mechanically, everything we will have to do at the level of Hilbert space, because there we have to do things. Now, this displacement is a continuous, this can be arbitrary, because q can be arbitrary, E naught can be arbitrary. So, this is continuous. So, when you displace your physical system, which is here a one dimensional harmonic oscillator. So, you displace it, right, quantum harmonic oscillator. If you displace it, which is a physical transformation, is a canonical transformation, then Wigner's unitary theorem tells you that there will be a corresponding unitary representation of this displacement operation on your physical system, and that representation is d alpha. See, in quantum mechanicals, in Hilbert space you cannot do physical operation, you will have to take the corresponding representation. So, that is what we have done. Okay.
This d alpha acts on the Hamiltonian to give the new Hamiltonian.
Yes.
Okay.
Yes. Equivalently, you can say that d alpha acts on the states to give you new states. Okay. I mean, eigenbasis of the original Hamiltonian, d alpha acts on them to give rise to the eigenbasis of the new Hamiltonian.
So, magnetic field, applying magnetic field will result in the translation along the momentum.
Along momentum. Yes.
So, if you apply both, then it will be in general.
It is not so simple. Okay, it is not translation. Okay, if you apply both of them.
Sir,
Yeah.
can you please repeat the theorem, Wigner's theorem again?
So, Wigner's theorem tells you, Wigner's unitary anti-unitary theorem tells you that if I do a symmetry transformation on my physical system, like translation, rotation, then scaling and some such thing, then there is a representative of this symmetry transformation at the Hilbert space level of this corresponding physical system, and this representative will be either a unitary transformation on your states or antilinear anti-unitary transformation on your state. Okay, right?
Anti-unitary means it can be some, let's say,
No, anti-unitary is not dissipative. Anti-unitary means that this, unitary means what? U dagger is equal to U dagger U is equal to identity, right? Anti-unitary means it has a negative sign. So, it is anti-unitary as well as anti-linear. Okay. Alpha u plus beta v, u v vector will go to alpha star u plus beta star v. Okay. Right. Okay. So, so now this displacement operator, this is unitary operator, this is unitary operator in infinite dimension, right. Now, let us take this one, trace of D of alpha. Okay. So, this is infinite dimensional matrix. Okay. So, how will I get this trace? So, trace of these is uh, one upon pi d square beta, because this is coherent state basis I can apply, d of alpha beta beta. Is that clear? Because the identity operator I have inserted. Okay. Okay. So, this is 1 upon pi beta belonging to C d square beta beta d alpha beta. No, this is, I discussed this thing, that identity, the same identity operator you can have coherent state basis representation 1 upon pi beta belonging to C d square beta projection on beta, right. This is the coherent state basis. Okay. So, now so I will have to now look at this expression. Okay. So, d of alpha is exponential of alpha A dagger minus alpha star A. Now, I use Baker-Hausdorff formula. So, Baker-Hausdorff formula tells me that if A and B are two operators such that both of them commute with commutator of A and B, then I can write e to the power A plus B as e to the power minus half commutator of A and B times e to the power A times e to the power B. Okay. So, for me, I take this B as minus alpha star A and A as alpha A dagger. Then what is commutator of A and B? This is minus mod alpha square A dagger A. So, which is just mod alpha square. Okay. And therefore, this condition will be satisfied. So, this d of alpha is equal to e to the power minus mod alpha square by 2 times e to the power alpha A dagger times e to the power minus alpha star A. Okay. So, now let us look at this expression beta d alpha beta, and why I am considering this, it will become clear later. Okay. Why I am considering trace of this. So, this is, if I use this formula, this is e to the power minus mod alpha square by 2, then this is beta e to the power alpha A dagger e to the power minus alpha star A acting on beta. Now, what is this? This is just your minus alpha star beta times beta. So, this is just I will replace this beta, and what is this one?
Alpha star
Right. So, this is basically your exponential of minus mod alpha square by 2 plus alpha beta star minus alpha star beta. Okay. Right. Okay, good. So, a trace of d of alpha, this will be 1 upon pi beta belonging to c d square beta, then what is that, exponential of minus mod alpha square by 2 plus alpha beta star minus alpha star beta. Okay. Is that clear? I think so, right? Okay, I think it is correct. Okay. So therefore, this is e to the power minus mod alpha square by 2 by pi, then beta belonging to c d square beta exponential of alpha beta star minus alpha star beta. Okay. Yeah, and this quantity is basically this 1 upon pi beta belonging to c d square beta exponential of alpha beta star minus alpha star beta. This is your 2-dimensional delta function. Okay. I mean, you can express it in terms of real and imaginary part and figure out this is your 2-dimensional delta function. Okay. So, what you see here is that this is e to the power minus mod alpha square by 2 into 2-dimensional delta function. Okay. So, this is your, so let me write it here, e to the power minus mod alpha square by 2 into delta 2 of alpha. This is my trace of d alpha, right. This is of course singular because it is infinite dimensional matrix, but that is okay.
So, for alpha not equal to 0, this is 0.
Alpha not equal to 0, this is 0. Yes, yes, exactly.
And for alpha is equal to 0, it's an identity matrix.
Kind of, yes.
So, it's an infinite trace.
Yes. So, now let us take, so now, so this is important for us. Now, we are going to talk about some sort of group properties of this displacement operator. Okay. So, let us take d alpha d beta, I mean product of two displacement operators. So, this is exponential of alpha a dagger minus alpha star a times exponential of beta a dagger minus beta star a. Okay. So, this I use Baker-Campbell Baker-Hausdorff formula, which tells me that this is minus mod alpha square by 2 e to the power, what was that, alpha a dagger e to the power minus alpha star a. Here I will use the opposite. What I will use is what is that formula? This is a and b. So, I will take this as b, this as a. What is it? What I have done here? Anyway, so that you know this b will appear later. Yeah, right. So, what will be that in this case? This is b, this is a. So, therefore, so this is e to the power minus half a b commutator times e to the power a e to the power b. So, what is the commutator of this? This is minus, so a and b is minus beta star a, then beta a dagger. So, this is minus beta square. Okay, so this will be e to the power plus beta square by 2, then e to the power minus beta star a, e to the power beta a dagger. So, let me put it here. So, this is e to the power beta square by 2, e to the power minus beta star a, e to the power beta a dagger. Okay. So, this will be e to the power half beta square minus alpha square times e to the power alpha a dagger e to the power minus alpha plus beta star a e to the power beta a dagger. Okay, right? And now I will use here alpha a dagger. So, what I need to do here is e to the power beta minus not alpha a dagger. What is the relation I should use? Here it is minus. So, here it should be alpha plus beta a dagger. Okay. Now, I should use this formula that e to the power a times b times e to the power minus a. What is that?
B plus A minus AB commutator of AB AB plus commutator of plus half commutator A comma A comma B.
Is that the one?
Yeah.
Becker, Hausdorff, Campbell.
Okay, maybe. So, how do you check this thing?
Expand, exponential, etc.
Yes. So, the first term is of course fine. What about the second term?
1 plus a b.
A b and then minus b, fine. What about the third term?
A square.
A b, it is minus a, right? And yeah, so what you will have here is a square by factorial 2 b, then minus this and then plus b a square by factorial 2. So, is that the one you will get? A square b, yes, fine, you should get this. Okay, good. So, this is what you will get. And here you do not have to assume anything like whether this should be 0 or not, you do not have to assume. So, now for this one, so we need to do it for, okay, so we need to do it for A first and then we can do it. So let us take A to be alpha A dagger and B to be just A, small a. Okay. So, then e to the power alpha A dagger times A times e to the power minus alpha A dagger, this will be A plus alpha A dagger comma A plus half alpha A dagger comma alpha A dagger of A plus so on. So, this is A minus alpha, and what about this? Plus half, this is alpha A dagger, and this is minus alpha, of course this is 0. So, therefore, this is what you will get, okay, A minus alpha, right. Okay. So, this is A minus alpha. What about A square by factorial 2 here? So, this will be, okay. So, what about A square? So, A is this, fine. So, what about e to the power alpha a dagger a square e to the power minus alpha a dagger. What about this? So, this is e to the power alpha a dagger a e to the power minus alpha a dagger times the square of this. So, this will be, so a square by 2 will be square by factorial 2. So, ultimately what you will get is, if I look at, so let me write it here. So, this is e to the power half mod alpha square minus mod beta square minus mod alpha square into what can I write about this?
Minus alpha.
You have to expand, I think.
A minus alpha kind of.
Is that the correct statement for this? I guess that is correct, right? Yeah, I mean you just take the powers of this is okay, good. Okay, now I should be a bit careful. So, this is exponential of half beta square mod beta square minus mod alpha square, and then from this side I will have plus this is alpha into this. So, plus mod alpha square plus alpha beta star, this is fine, then exponential of minus alpha plus beta star A exponential of alpha plus beta A dagger. So, something like this, right. So, therefore, what we need here is e to the power mod alpha plus beta square by 2. So, this is exponential of half. So, this is mod alpha square plus mod beta square plus alpha beta star, and now I need this. So, basically this is half alpha plus beta whole square, then d of alpha plus beta, okay, right, because you know this is the expression for d of, so this is for d of beta. Okay. Now, what will be this? This is exponential of alpha half of alpha beta star minus alpha star beta d of alpha plus beta. So, what you get is d of alpha times d of beta is this expression. So, this is just a phase times d of alpha plus beta, right. Okay. So, basically these displacements get added up to this phase.
It's actually an easier way, I think, to prove this from just the first equation. If we let the the term inside the first exponent be a and the term inside the second exponent be b.
Yes.
So that whole term alpha a dagger minus alpha star a, that is a, okay, capital A.
Yes.
The other thing is b, that will satisfy this one here, the condition for Baker capital.
Yes.
Then what we have is e to a, e to b, and if you take that minus half commutator of ab to the other side of the equation, then you have e to a plus b into e half.
Yes, you can also do that. Yeah, that will be easier.
That's easier.
Yeah. Yeah, that is true. Yes. Okay. So now, so let me use this now. Okay. So you see that. Okay. So basically, let me look at once again this thing. D of alpha dagger, D of beta, trace of this thing. So this is trace of d of minus alpha, d of beta, right, because d of alpha dagger is d of minus alpha, and this according to whatever I told you earlier is this is trace of beta minus d of beta. No, there is a phase factor. What is that? Alpha star beta minus alpha beta star exponential, then trace of d of beta minus alpha, right, and this is exponential of. Now, what about this trace? This is minus half alpha minus beta whole square plus half alpha star beta minus alpha beta star, this should be alpha beta star, then delta 2 of alpha minus beta, right. Okay. And this you know that what will be that? This is minus alpha star beta and then plus, no, what is that? First term will get cancelled. Yeah, anyway, so you can keep this thing, it's fine. So, basic point is that so this displacement operators, they are kind of orthogonal, okay, right, is that correct statement? Yeah, they are kind of orthogonal because of this delta function, right, unless I have messed up this factor, hopefully not, but because of the delta function you see that the displacement operators, they are kind of. So, this is what we we use for the Hilbert-Smith norm, okay, Hilbert-Smith inner product of operators, this one. So, therefore, this tells you that the set of all displacement operators where alpha belonging to C, this is a kind of orthonormal basis. Well, orthonormal is bit tricky, but at least orthogonal basis you can say.
If we take alpha is equal to beta, then it will be delta of 0.
That is okay, that is fine.
That is 1.
Delta of 0 you cannot say 1.
Infinite.
Infinite. Okay. So, this is an orthogonal basis, right. As a result, I can express any bounded operators f, bounded in the sense that if I take its norm like Hilbert-Smith norm, it should be finite. Okay. So, if I take any bounded operator, then I can express it as d of alpha times some function alpha. So, this function of course depends upon this f operator, right. So, this I can always write, any bounded operator can be written as a linear combination of these displacement operators. Okay. Yes, kind of. So, but this is for you take any bounded operator, this can be, because this forms a basis, this displacement operator. So, you can in principle write any bounded operator as a linear superposition of this displacement operator. Yes.
Is there Requirement of boundedness of the function f of
Yes, so this will come later. Yes, so what you can do is the norm of this function will be same as norm of this operator.
And what is the issue with unbounded operators being represented by this?
So unbounded operators, you will have problem with the convergence of this. So that I cannot talk about. Okay, so I mean, some unbounded operators will have this representation, but I'll have generically convergence issue of this integral. Okay. So what about this f of alpha? So let us take d of beta or maybe I will take trace of f d of beta. So this will be alpha belonging to C d square alpha trace of d of alpha d of beta, then f of alpha. F of alpha is a scalar function. Now what is this trace of can I get something from here? So what is that? This is alpha belonging to C d square alpha see, this I can write as this part I can write as iota imaginary part of alpha beta star, right. So this I can write as exponential of iota imaginary part of alpha beta star, then trace of d of alpha plus beta, then f of alpha, right. And what is trace of alpha plus beta? So this is your d square alpha, alpha belonging to C, exponential of iota imaginary part of alpha beta star, then this is what is this trace? Minus half alpha plus beta mod square, then delta 2 of alpha plus beta, then f of alpha, right. So this means that alpha should be equal to minus beta. So what we will get is imaginary part of minus mod beta star, which is 0, right. This is 0 and this is also 0. So this will go out. So basically what we will have if f of minus beta, right. Okay. So as a result you see that f, therefore f is equal to alpha belonging to C d square alpha d of alpha, then f of alpha is this. So what is that? This should be trace of f of d of minus alpha, okay, right. Or if you want, you can write it as d of minus alpha and this is d of alpha, same thing. Okay. So for any bounded operator, this is what you will see in terms of displacement operators.
What is that E in the first equation? E, capital E. Oh, that is F.
Which is there?
Oh, sorry.
Oh, this one, sorry, F. Okay. So now, you see that I mean, what is the relation between this norm of f, operator norm, okay, and the norm of this function, right. So, norm of this function means function, you know that this is so this norm of this function is what? This is equal to square of this is alpha belonging to C mod f alpha mod square d square alpha, right. This is the norm, right, or you can say this is to the power half, same thing. Okay. And what you can prove, and what about the norm of this operator norm? So, this operator norm is your trace of f dagger f, okay, then to the power half. So, this is the Hilbert-Smith norm. Okay. So, what you can prove is that these two are same. For any bounded operators, these two are same. And what is your f that I already discussed? What is your f? So, f of alpha is equal to trace of f times d of minus alpha, right. So, using this expression, you can prove that these two are same, provided f is a bounded operator, right. So, this is a kind of thing we already discussed earlier, that no, this is an operator. Now, you can take, for example, for d alpha, you can take normal ordering, anti-normal ordering, symmetric ordering, whatever you want to call, and correspondingly you will have to take here, and then you see that trace of rho and f. Okay. So, this will be basically alpha belonging to C d square alpha trace of rho d alpha times trace of f d of minus alpha.
Sir, what do you mean by they are same? I mean the function norm and
These norms are same. Functions are of course not same, because this is a scalar function, this is an operator of function.
so I mean we are expanding f
Hmm.
in terms of d alpha times f of alpha.
Right. And f of alpha, you already got this expression.
Yes.
And now, if you calculate the norm of the small f using this formula, okay, and f is the trace norm, I mean Hilbert-Smith norm actually, okay, then you can show that these two are same.
This is similar to like mod of the coefficient, this small f of alpha.
Hmm.
So this is similar to like coefficient, right?
Coefficient.
Coefficient.
Coefficient. Ah, yes, coefficient. Yes.
So the norm of that coefficient is equal to the norm of that operator.
It is not the norm of that coefficient. You will have to take this is a function. You will have to take this norm. Yes. Okay. So here you remember, this is what we have seen earlier, that I mean this is a kind of okay. So this is if you take for example, normally ordered operator, then this will. So, okay, so let me try to recall. So, you know that if you look at the p function p of rho alpha alpha star, which was no, I'll write this rho. So, this is alpha belonging to C, this square alpha p of rho, then alpha alpha, right. Okay. And then if you take any operator O which is normally ordered, sum over n m is equal to 0 to infinity, like C n m a dagger to the power n a to the power m, then trace of rho O n a dagger, you know that it can be expressed as d square alpha, this p rho alpha alpha star, and just this function where you replace a and a dagger by alpha and alpha star. Okay. So, it is something similar in the sense that this will be, well, it is not exactly that, but this will be somewhat similar to this function. I am not saying this is equal to this, something similar. Actually, the equality will occur when I take Wigner function, and this part is something similar to this. Okay. This is not exactly same, but something similar. For Wigner function, these are same. Okay. Right.
function means instead of p rho you are taking
Yes. So, for Wigner function, I will have to take the symmetric ordering, and then if I take, so if I take any symmetric ordered function a dagger, which is sum over n m is equal to 0 to infinity, let us say something e of n m, then a dagger to the power n a to the power m, this is symmetric ordering, okay, symmetrically ordered. Then from there you can see that trace of rho and O s a dagger, this will be equal to alpha belonging to C d square alpha, the Wigner function of the state multiplied by O s, just you replace alpha a by alpha, a dagger by alpha star. So, in fact, the Wigner function will be basically this one, trace of d alpha, rho d alpha. Okay. For other phase space distribution function, this is not so simple, but we will have similar expression. Okay. So, so you see that these displacement operators, they form a basis of operators, orthogonal basis, and you can express any bounded operators as a linear combination of the displacement operators. Okay. Now, in order to express, now why I am interested in this, because this is what we calculate in experiment, right. You have operator and then you take the expectation value. Now, in order to express this expectation value, not in terms of just Wigner function like in p function, q function, etc., we need to introduce a more general version of these displacement operators. So, this will not be sufficient, I will have to introduce something more general than that, and this we call we denote as d of alpha comma s. S is a complex number, alpha is also a complex number, and this definition is d of alpha times exponential of s mod alpha square by 2. Okay. So, s is a complex number, alpha is also a complex number. Okay. So, this is my new definition of this is a modified, or you can say S parameterized displacement operator. So, d of alpha 0, this is d of alpha, and this corresponds to symmetric ordering. So, S value 0, d of alpha plus 1, this is d of alpha e to the power mod alpha square by 2, this is called normal ordering, and from here you can guess that the corresponding distribution function will be Wigner function, this will be P function, and d of alpha minus 1, this is d of alpha e to the power minus mod alpha square by 2, this is anti-normal ordering. And this gives rise to the Q function. Okay. I mean it is not necessary that you will have to take S values only these 3, you can take any S value, any complex number. Okay. Now, what can I say about well, trace of this thing is of course very simple, trace of d of alpha s, this is your, what will be that, e to the power s minus 1 by 2 mod alpha square, right, times d 2 of alpha, right. What about d of alpha s and d of beta s prime? Again you can figure out, it is not difficult, but what about this? Beta s prime. Well, before that, what will be this one? This also you can figure out from here, okay? This simple definition, and you can take trace, etc. So, my point is that these are also, they also form an a orthogonal basis, right. For fixed S, they will form orthogonal basis, okay. And so, you can express any bounded operator again as a linear superposition of this d of alpha s and then some function f which I am calling f alpha s, okay, and you can figure out what is f alpha s by the same way what we have done. Yeah.
Without an S,
Yeah.
these were unitary operators corresponding to a symmetry transformation.
Yes.
of
So, this is
translation.
no longer a unitary operator,
These are not.
no longer a unitary. I mean, this you see that if S is a plus 1, when if S is positive, then this will basically enhance the kind of amplitude, okay.
So if there was no mod of alpha square, no,
it is not unitary. Okay. It is unitary only when s is equal to 0. Okay. So, but that is okay, that is fine, still it will form orthogonal basis and you can express any operator in that form. Okay, good. So, now what we need to look at is we need to figure out the. So, for Wigner function we have shown that if I look at the trace of rho and f, you have a statistical expression for that. For p function, q function and even all other s ordered function also you can get similar expression by using this modified operator, not the displacement operator, and this is what let me tell you now. So, I will be following this I told you these two papers by Cahill and Glover. So, this is what I am going to follow. Okay. Just a minute. Okay. Yeah. I mean this will be, it will be good if for you if you go through these two papers, read them carefully and try to derive things. It is a bit monotonous, but still this is quite helpful. Okay. Okay, good. So, I introduce this modified operator, and now what I will do is I will introduce a Fourier transform of that modified operator T of alpha s. So, this is beta belonging to C, d of beta s. So, for any fixed s, exponential of alpha beta star minus alpha star beta 1 upon pi, and this is d square beta. So, this you see that it is a complex Fourier transform of this modified displacement operator. This is my new operator T of alpha s. Okay. Why I introduce it? Because this will be helpful to figure out the characteristic function that I mentioned last class. Okay. So that will be useful for me. Okay. Right. So, now if I want to write alpha f, so f we have written in terms of d s, but now I want to write it in terms of this T of alpha s, that also I can do, because when they form orthogonal basis, they will also form orthogonal basis. Okay. So,
What does this mean to act this operator d alpha comma s on a state?
yeah, this is
Factor e to the power s.
this is just a scalar factor. So, this is basically displacement multiplied by the scalar factor.
So that scalar factor can always be normalized.
You can, but before normalization what it tells you is that it changes the norm of the state,
Yes.
right, and therefore it is not a unitary transformation. And this is important because p distribution I told you that this is very ill behaved function. Okay. So, this factor by suitable choice of s when you do, this will kind of tame the behavior of the p distribution. If you choose s negative enough, it will tame the behavior of this p distribution. Okay. Or vice versa, the q distribution is well behaved, but if you want to go from q distribution to p distribution, you can choose this s to be positive enough.
So this p distribution, because S is positive,
Yeah.
for large alpha, the magnitude will be infinite, diverging.
Exactly. That is what it happens for most of the states. P distribution is highly singular. Okay. Okay, good. So now I can write it therefore in the same fashion which I have done for the displacement operator. So I can write it as alpha belonging to C d square alpha. Now let me call it T of alpha s, this is my operator, multiplied by f of alpha minus s, okay, and then 1 upon pi, and then yeah. So this is what so this is my weight function corresponding to f for given s, and this is this operator, okay, right. And you can now figure out so what is this function f of alpha minus s, what is that? This we know. So this will be, as we have seen earlier, this will be f of t times alpha comma minus s. You understand, this is we have done for the displacement operator. Here also you can do the same thing. So you first write f in this form, and then you can figure out that f is of this form. Okay.
So why did you take this f of alpha comma minus s?
Yeah, so because I have taken this new set of operators which is s dependent, which are s dependent. So my weight function should also be s dependent in general.
That is okay, but why this negative sign?
Why this negative sign? Yes. So you know, this you can take as your definition of f, this capital F, and then you multiply this trace of f, then t of, here it is alpha, let us say beta and s prime. Okay. If you do that and use these properties of this modified displacement operator, you will get this operator, just the same way we have done earlier. Okay. Okay. So, so therefore, any operator, of course, this has to be kind of bounded. In fact, this is also, one can extend it a bit more. You do not have to take it to be bounded always. What you can take is it is trace class operator. So, trace class means trace of f has to be finite, or maybe mod of trace of s has to be finite. So, this is trace class operator. Okay. So, so this relation holds good not just for bounded operator, but also for trace class operator. Okay. Right. Okay, good. So, now you can take a form of this f, okay, and so which is basically your s ordered form. So, let me write it first, okay, so then things will be clear. So, what you can do is you can write your f in this form, n m is equal to 0 to infinity. So, I am writing in terms of a and a dagger. Okay. So, this is a dagger to the power n, a to the power m. Now, this is s ordered. What is this s ordered? For S is equal to plus 1, this is normal ordering. For S is equal to minus 1, this is anti-normal. That means a dagger a to the power m, a dagger to the power n. For S is equal to 0, you will have to symmetrize it, symmetric ordering. Okay. General S, of course, it is not so simple, so it will come in the following form. So, let me first write it and then things will become clear, I hope. So, this is your S ordered form, right. This is n factorial m factorial, and then you do this thing del n plus m f of alpha minus s divided by del alpha star to the power n del alpha to the power m, right, and then you take its value at alpha is equal to 0. Okay. So, you take any operator f which you can write in terms of powers of a and a dagger, right. F corresponding to this capital F operator, which you find from here, and then you take this expression for f. So, basically this will be again a combination of powers of a and a dagger, but what is that combination? It is that combination which you, when you take with this coefficient, it will give your f. So, it is a bit complicated thing, but we do not have much choice. So, for example, so you will have to go by example. So, if you take S is equal to 1, this is your normal ordering, already it is there, right, and then you can figure out. So, f, it is up to you how to write f as an operator. You can write it in terms of normal ordering, you can write it in terms of anti-normal ordering, whatever you want. So, this is basically when you write f in terms of S ordering. Okay.
This f small f alpha.
Yes.
There is always assumed that it's a function both of alpha and alpha star, because you are taking derivative with respect to alpha star also.
No, I am not taking derivative with respect to A star. It is see here in all these calculation, what you need to assume is alpha and alpha star are independent parameters. So, that is why you will have to take this. So, in other words, in all this calculation, if you take del alpha star of del of alpha of some function, whatever be these functions, this will be 0. Okay. I mean, you understand. So, these are independent variables. No, that is fine. I mean, if you, so my point is this alpha and alpha star are independent variables. Okay. That is what I want to say.
Okay, then what about your integration? You always write this d alpha, right? d2 alpha.
Yes.
So there it's
Oh, stock is there, huh? Okay, sorry.
should not it be d alpha star for the integration case? I don't know. I mean, you told that alpha and alpha star should be there.
No, you do the two-dimensional integral x and y. Don't you take them independent?
Yeah, but what about this integration?
Which integration?
Let's say
D square alpha.
yeah.
There is no alpha star in the integrand.
Should not it be
Yeah, maybe you can explain. Yes.
I mean, like you write d square x as dx dy, right? It's like that. D square alpha is d alpha d alpha.
yes.
Yeah, so it's the same thing. Does that make sense?
Yes. So, this D square alpha, this is d of real part of alpha times d of imaginary part of alpha.
Oh, okay.
It is not. Okay, maybe I should stop here because there is a seminar. So, I will start from this expression once again, and that so I will give some example. to I cannot give a general expression for S, this is impossible. So, I will give you some example for this, and then from then that onwards I will move, okay, move forward.
Okay, so the goal was to write this F in terms of A and A dagger.
Exactly. So, basically whatever ordering you take, accordingly your weight function should be decided.
Except for the case of 0 plus minus 1, are we interested in other, experimentally, would we be interested in other S?
Sometimes not well, experimentally we do not know what are their importance, other S values, but for certain calculations other S values are important. Okay, thank you.